Hi everybody. After completely tearing apart 4 different large analog meters of different manufacturers and different types, we're going to have a look at one more here, and this is one of my favorites because it works beautifully and it has very unique movement inside. It is an electrostatic voltmeter, completely different from the others because this one measures voltage directly as a voltage. There's no current draw, at least in DC. We'll get into that soon. There's no DC current draw with this thing, whereas the others have to have at least a tiny amount of current for them to work, to send a needle pointing up on the scale, because it needs a current going through a magnetic field. This one is all electric field in here. So this is Sensitive Research Instrument Corporation model ESD. Got 1% accuracy guarantee. There's even a temperature correction coefficient on this thing, and frequency range from DC up to 1 megahertz. And we'll have another look at that soon. Standardized by Lewis Miller on, if we can see that, July 1st, 1954. And here's the front panel. Again, Sensitive Research Instrument Corporation, Mount Vernon, New York. And a very non-linear scale, up to 5 kilovolts. There's some other information there. And ranges, ESD, and capacity, 33 to 35 microfarad, because they didn't have picofarad back then. It was just microfarad. So let's take this front cover off, the top cover, and we'll start taking out these screws. Now, I'm not going to give this thing a complete tear down like I did the others, because I really just want to maintain this thing in perfect working order. And I have had this thing apart several times before. This screw right here is where the calibration seal used to be. And I've even wanted to do a video like this probably about 2 years ago when I was doing all my Tesla coil stuff. I even used this thing with a great big voltage divider network in a futile effort to try to measure the voltage on top of my Tesla coil. So let's pop the hood on this puppy and see what we got. Let's have a look at this first. See, we got this nice aluminum foil shield all around the outside here. And again, we've already seen this before. This is just to prevent any kind of electrostatic potential building up that could potentially affect the reading, attract the needle through electrostatic forces. And that would be especially possible with something like this. So here she is in all her glory. Nice and shiny stuff in here. So if I move the needle right here, you can see that the only moving part really is this one piece of aluminum in here that's got a couple of fin shapes on either side. And you might think that that's the part to be energized to high voltage, but no, it's actually part of ground, or at least the shield of the whole thing. You can see that it's got a metal shaft going from here down to the moving aluminum plate, and then continuing down to the bottom aluminum plate down there, supporting the whole structure. And that whole thing is right here on this wire, going over to this terminal, which is labeled low side or ground. We got these nice insulating terminals here, and I've hooked up already this copper ring terminal, which I cut out a slight portion of that ring so I can easily slide it on here, and also wrapped up the end of it, which would normally be crimped on a wire, but wrapped it up just at the right diameter so it can easily stick a banana jack into there. Now the terminal that does get energized, or at least should get energized, is the high side here on this clear plastic insulator, and that comes out through the box and hooked up to the 2 stationary plates just beneath the moving plate. So there's one plate right there, and then it's got this nice looping wire going all the way around here to right there. So if you haven't guessed it already, this moving ground plate gets attracted to the stationary high voltage plates completely electrostatically. There's an electrostatic force that just pulls it ever so gently over that way across the range of the meter. Now, one disadvantage of this kind of voltage measurement is that the scale is really non-linear. Up here in the middle of the scale, we've got pretty good deflection of degrees per unit volt going into the device. And even up here at the top of the scale, we've got 5,000 volts and 4,000, 5,000 volts. It's a pretty decent scale up there. You can actually measure individual units down to, 50 volts. Each single line that you see here is 50 volts worth. But down here at the bottom end, we go from 0 to 1,000 in a matter of 2 millimeters. So really, really poor at low voltages. And that's simply because of the nature of electrostatic attraction. With the physics going on here, the force being applied to these plates, the torque, is proportional to the square of the voltage. So tiny amounts of voltage result in slightly larger squares of that voltage. But as you increase the voltage, then the square increases much, much faster and higher. And of course, that's going to give you a much greater force to overcome the torque of the spring in there. There's a good view of that return helical spring. Now let's have a look at this capacity measurement here of 33 to 35 picofarads as measured back in 1954, 61 years ago. Now when I measured this thing with two different digital LCR meters, I got pretty much the same result of 12 picofarad, give or take half a picofarad or so. Not that much of a difference, and that's going straight across these two terminals into the box. Doesn't matter what the polarity is because it's an AC measurement anyway. And I got 12 picofarads, and even if I gently move that needle either with my finger or with some kind of insulated plastic rod or anything like that, it really varies anywhere from 11 to 12 picofarad regardless of where I put the needle and the corresponding plates down here. That's going to certainly change the capacitance, but not by much, only by a picofarad or so. Even if I put the top plate back on top with this extra shielding in place, making contact with these 4 aluminum foils down here, then that's not going to affect it much either. Again, that might just add half a picofarad or so. Trust me, I measured it. It's really about, on average, we're looking at 12 picofarad for this thing, no matter what the position is for the needle. And this is not news to me. I've actually made this measurement many times and many years before, and we can show it with this Fluke 867B right now, just with the probes hooked up to the input down here. We've got 130 picofarad, 120, 130 picofarad, 140. Well, that's just because I'm moving this thing around and it's becoming closer or further away from the black lead here. We let it stabilize out maybe, and we'll just plug it right back in here. And there we go. It jumped 10 picofarad up because that's the closest precision that it can get, down to the 10 picofarad range, not the 1 picofarad. But yeah, roughly, 10, 12 picofarad. That's how much we got here. Certainly not 30 to 35 picofarad. And for the longest time, I thought that there was some error in Lewis Miller's measurement back in 1954. But I think he knew what he was doing, and it's just a factor of age that has caused the capacitance of this thing to decrease. And I can show you why. Take this out. And that's because it's coated on the interior with all of this conductive paint, or at least paint that must have been previously conductive, because we do have these aluminum sheets right here and going into the screws. But basically these aluminum sheets make contact on 4 points, 4 corners here basically, with the aluminum shield on the front cover. And there's the matching 4 aluminum sheets right there. Just foils really, just wrapped around and then painted over with this conductive paint. And you can see that the paint comes down here to this, to the thick metal washers here for the low side or ground input. The high side is very thoroughly isolated from that. We've got no conductive paint anywhere around there. And then the paint continues up around there and basically all around the inside of the box. Unfortunately, this paint, after 61 years, is not quite as conductive as I assume it once was. So let's measure some resistance here. I'll plug this straight into the low side or the ground. I don't really have to hold it down. It's just, touching the copper. That's going to be a low enough resistance compared to everything else right here. Because if I just touch it here, there's nothing. And I can touch it down here to the ring where this thing is connected. There we go. We got 0.15 ohms. So clearly pretty good connection with the black probe. but touching the aluminum foil here, touching the paint, even touching the paint, oops, gotta be real careful. Oh, what did I do? Oh man, whew. Gotta be careful there. I just bent the needle down underneath the scale. Gotta make sure that's still good. So I'm gonna very carefully touch the paint just outside of the thick metal washer right there, and we still got nothing. I'm gonna have to figure out what the maximum scale is on this thing. I see a 30 megohm right here. I guess we're on the 30 megohm scale, and we're certainly well in excess of that in resistance. Now I can even take the two probes here and just poke them right next to each other, just a couple millimeters apart on the conductive paint, and there we got pretty decent 44 ohms. I'm surprised there. Stick it over here a little bit. 76 ohms. Wow. Over here to the aluminum plate, 97 ohms. So the paint is quite conductive right there. What about on this side? Huh, look at that. May as well be infinity. You poke it even closer. 2 kilo ohms, 1. Oh, now they're just touching each other. Yeah, it's just really finicky here in some places. Well, this is quite strange. I've measured on this board right here and on this board right here, and anywhere between the probe points is on the order of hundreds of ohms, tens or hundreds of ohms on this side and this side. But on the other two sides, on here and on here, I can get, you know, put them so close together, really jabbing the probes into the wood, still in excess of what the ohm meter can actually read. Let me poke it down here on the bottom, because we do have conductive paint on the bottom of the board, the bottom of the box. Still nothing. Well, anyway, I don't know why, but apparently time has been kinder to some parts of the shield than it has been to others. But ultimately, the whole shield is pretty much lost. There's really not much contact at all with the ground terminal here, and that would account for the much lower capacitance that I measured today than what was very likely measured back in 1954 with the 35 microfarads right there. So the 12 picofarad I measured today, that's just because of the plates down here, the active parts of the device. That's just the capacitance between them, 12 picofarad, and that's what I'm working with, and that's fine. I mean, if I don't have any concerns for shielding, then lower capacitance on this thing is always going to be better, because then I can measure higher frequencies of voltage, higher frequencies of AC voltage, that is. Remember, we saw that it goes to 1 megahertz, or back then it would have been cycles per second, but they just put a little sinusoid symbol right there. Now, if we do the 1 over 2 pi FC, in this case 1 over 2 pi 60 hertz times 12 picofarad, we get a impedance of 221 mega ohms, and that's pretty good. I mean, typical DMM like this for most voltages is going to have 10 mega ohm impedance. If we increase to 1 kilohertz here, then we get 13 mega ohms, and that's also pretty good. But if we go up to 1 megahertz, then we're down to 13.26 kilo ohms. And of course, that'll be just fine for low impedance systems, but if you have some very low current, very high impedance voltage source, that might be a problem. By the way, you may have noticed that on my trusty TI-89, I've got an M and a P in here. That's just mega and pico, 10 to the 6 and 10 to the negative 12. And that's just how I enter in my exponential information, or at least the most common exponent values that you would typically find in engineering. So I've got femto, giga, kilo. No, I don't bother with kilo. That K is blank. But I do have mega, nano, pico, and micro right there for the U. So I just find it much easier to enter in the alphabetic character for any given engineering multiplier, rather than doing the exponent and then maybe the minus sign and then 2 other digits on here. It's just easier to do alpha, number, and that's it. You got it typed in. Okay, got it put back together. That's as far as I'm going to go with the teardown explanation of this thing. I'm surprised that there's really not a whole lot of information out there, especially on YouTube. There's only a couple of videos where the people describe it just a little bit and how it works, but they don't go nearly in depth as I have done to tear the thing apart and explain how it works. So I hope this was quite helpful. If you learned something, please give this video a thumbs up, and I've actually seen these things on eBay too. You can get something like this for about 50 to 100 bucks. Sensitive Research Instrument Corporation, that seems to be the dominant brand for these electrostatic voltmeters, and they've, you know, anywhere from the $50 to $500 range, depending on the type and the construction of it and how high of a voltage it actually measures, and just how demanding the seller actually is. I think 500 bucks for any of these things is a little bit overkill, but that's what they're going for. Not this particular type. I saw one that went down as low as 300 volts. So instead of 5 kilovolts, it was a 300 volt full scale. And of course, that's going to have plates on the inside that are much closer to each other, maybe only half a millimeter or so instead of a full centimeter or so that we saw in here. And also they got higher voltages like 10 kV and 50 kV and various different constructions, where instead of looking down on a needle pointing like this, you'd be looking sideways on a needle that moves in an arch like that. Completely different topologies. Have a look, see what's out there if you really want to get one of these. So I've decided to cut it off here. I've done tear down and explanation of how this thing works.